And actually, I'm really happy that Saul is with us. So he's from Indiana University, and we have started to communicate a few years ago, I think, right? Yeah. But at this year, we started to communicate more intensively, and I'm really happy that there is a chance for Saul to give a talk on the workshop about some results concerning generalized pancake graphs. So the floor is yours, please.
Thank you very much for the invitation. Do forgive me if I seem like I'm slower than usual, because it's like, for me, it's like 8 a.m., which is unusually early for me. And this is all joint work with my collaborator, Charles Burley. I always mispronounce his name, but I think he's with us as well. And in just an advertisement, he will give a talk tomorrow. So I'm hope that we can attend and provide suggestions, because it's also like an open, we have many open questions in that area. And we need somebody who knows the field better than we do. Anyway, so let me talk about the girth and length of cycles in generalized pancake graphs. So the standard, the motivation for the whole project, I mean, it's been a while since, so the original statement of the pancake problem showed up in 1975 in the problem sections of the American Mathematical Monthly. This is the problem itself. So let me just read it. So the chef in our place is sloppy, and when he prepares a stack of pancakes, they come out all different sizes. Therefore, when I deliver them to a customer on the way to the table, I rearrange them so that the smallest one's up on top and so on down to the largest on the bottom. By grabbing several from the top and flipping them over, repeating this, varying the number I flip, as many times as necessary. If there are n pancakes, what is the maximum number of flips as a function of n that I will ever have to use to rearrange them? So I can illustrate the question with with this particular example. So you have a stack of pancakes, and they all have different sizes. And what you do is, you have this like spatula chef spatula that is only allowed to, you can only grab something from the top and flip them over. So in this particular case, the result of flipping the top 3 pancakes is illustrated here. So essentially, you just grab the top 3 from the top and you put them back, flipped. So of course, we need some kind of notation, because like whenever you can ask a computer to like think of a stack of pancakes. So instead we will use permutations, right? Because every pancake, all the pancakes have different sizes. So it is you can represent the stack using a permutation. So in this particular case, you read from top to bottom, like this is 2, 1, 4, 6, 3, 5. It's supposed to be representing the relative size of the pancakes as you look at the stack from top to bottom. And the result of flipping the first 3 pancakes in this particular case is the same as reversing the first 3 characters in the permutation. So this is the setup of the problem, and then from here we'll get a graph, and then we'll do more. We'll get all the graphs too. But just when it comes to the pancake problem itself, the pancake problem is: can you tell me the minimum number of flips that you need to sort any stack that has n pancakes? So it actually it's a difficult problem to do computationally. So only a couple of values are known. Precisely what they are. So if you let Fn be the least number of flips to sort the worst case stack of n pancakes, only the following values seem to be known. So you can see, like, if n is 1, well, the pancake is only 1 pancake, so it's already sorted. If you had 2 pancakes in the worst case scenario, they're out of order, you just need 1 flip, and so on and so forth. So these are the numbers. As you can see, they grow very, very slowly, right? So like, all the way up to 19, for 19 is 22, but you can see the numbers growing very, very slowly. It's 0, 1, 3, 4, 5, 7, they grow really slowly. However, it is actually very difficult to determine what the number itself will be for a specific n. You can get bounds, and of course I'll talk about them, but to compute the number precisely is actually computationally intractable. So I can talk about ways of solving the problem. So that was the original statement here. And then they provided one solution, which wasn't the most efficient solution. But anyway, so the solution they provided was this one. So one way of sorting the stack would be you take the largest, you go from top to bottom, look at the largest pancake that is out of order. Then you use one of your flips to put the pancake on top. And then you do another flip to put the pancake in the respective place, what it should be. For example, let's apply this largest pancake first algorithm to this stack here. So this one is the one 2, 4, 1, 5, 3. So the largest pancake that is out of order is this 5 right here. So the first thing we'll do is flip, we will try to flip it over there. So we put it on top, and then that will give us that permutation, right? And now what we do is put this one, put this 5 pancake, the pancake label 5 in the respective place, which should be at the very bottom. So then we grab the whole stack and we flip it. And we do this again. So now the 5 is in the right order. So now we take the largest pancake that remains, that is not in the proper order. That would be the one labeled 4. So we try to flip there. So we put that one to the top first, and then we put it in a respective place. And then so on and so forth. So now we take the largest pancake that is not in the right order, which is labeled 3. We put it on top, and then we put it in the right place. And so on and so forth. So I want to thank Charles for these beautiful animations, because they're very, LaTeX is wonderful. You can do these wonderful things. He did it at some point, and I'm just borrowing from him. Okay, so that's one algorithm. So that gives you one bound for the pancake problem, for the pancake number. But of course, things that are more complicated. It's not the most efficient algorithm. And then in this particular case, you have a sequence of a step that took 7 flips, but it's not the most efficient procedure in this case. For example, for the same stack, you can do this other procedure that kind of starts the same, but eventually diverges a little bit. And then it gets to, this one just took 5 flips. So the naive algorithm that I mentioned at first is not the most efficient one, but it does give you a bound, of course. So what is known, some bounds for the number? So obviously the one I just mentioned is about 2n. So like, you take the largest pancake that is not in the right order, you put it to the top, that would be 1 flip. Then you put it back in the right place. Then that would be another flip. So for each pancake, there's about 2 flips. So that would give that algorithm will be the largest, flip the largest pancake out order would take about 2n steps. And then there was the first, so the first non-trivial bound that showed up was in 1979, and this is Bill Gates from Microsoft and Christos Papadimitriou, who's a very famous computer scientist. And their bound was 5n divided by 5n plus 3 divided by 3, which is about 1.666 n. As you see, I mean, so there's an improvement from 2 to 1.666 n. So it's a pretty nice improvement. And then later on, so this is a picture from one of our textbooks that we have used in the past. We have a bioinformatics class here, and this is one of the pictures that showed up in the textbook. So this is Christos Papadimitriou, and then this is Bill Gates, and they're flipping pancakes. It's pretty neat. So obviously, the pancake problem has some connections to bioinformatics that I mentioned briefly. But yeah, the reason why it shows up in a bioinformatics textbook is because of the connections of this kind of sorting to genome sequences. So then at some point in 2008, there was this team from Texas, and you can see them right here smiling very proudly, that made an improvement from the 1.666 bound that I mentioned. So it took about 30 years, a little more, I guess. And they put it in the news in their university. So their improvement is this one. So 18 divided by 11, so it's about 1.6363. So, and so far I think this is the best upper bound that we have. So what else is known? Well, in terms of lower bound, this is simple lower, the trivial lower bound is actually n. And the way you think about this is by like, if you consider stacks of pancakes, when you have consecutive pancakes that need to be separated, then you have to put, like in this particular case, you look at this stack here, 5, 2, 4, 1, 3. Well, the 5 and 2 will end up in different places. They won't end up next to each other in the final, when they are sorted. Similarly, the 2 and 4 won't end up next to each other when they're sorted. The 4 and 1 won't end up next to each other when they're sorted. And so in the same for the 1 and 3. So because they won't end up, the stacks of pancakes here, the consecutive ones won't end up next to each other, then you have to separate them with a spatula flip at some point, right? So in that case, you'll need at least like n-1, I suppose. You can always come up with a stack like this. So the lower bound would be n. It's actually, you can actually improve it, but I'm just saying like this is one. This pancake bound. This pancake number grows very slowly. It's at least n and at most to n, and actually you can do better, like I mentioned. So it grows really, really slowly. However, it is proven that they're actually determining the specific pancake number is an NP-hard problem. So it showed up in 2015, and this is I think it's a French team that showed up that computing the actual pancake number is an NP-hard problem, and it showed up here in this journal. They're all from Nantes. Actually, we're going to have one of them give a talk for us. He's going to give a talk in our seminar and our colloquium later this year. Anyway, so there are two common applications that people talk about when it comes to pancake sorting. One of them is genome rearrangements, and the other one has to do with parallel processing. And this is more classical now because parallel processing has changed significantly since the time of interconnection networks, which pancake graphs is given as an example of, as a model of. But these are the two connections that people care about this type of sorting, at least from the computer science point of view. So how do you get a graph from the description I just mentioned? So essentially what you do is you have the permutations as set of vertices, and you connect two permutations with each other if there's a prefix reversal that will transform one permutation into the other. So what a prefix reversal is you essentially take a prefix of the permutation. So the prefix is, again, a substring that goes from the beginning to some position I, and then you reverse it. For example, if we look at this 2143 here, then you can see that we can reverse the first two characters, and that will give us 1243, which is here. Or you can reverse the first three characters, and that will give us 4123, which is this one. Or you can reverse the whole thing, and that will give you 3412, right? So you can get a graph in this fashion. So, and again, one of the reasons, I mentioned this, but one of the reasons why people care about in computer science back in the 90s about these graphs is because you can think about them as a model for interconnection networks. So what they are is essentially, you imagine each of the permutations being like a CPU or some kind of processing unit. And then you think about the edges as way of saying these two CPUs communicate with each other. In this particular case, people care about cycles. For example, this is the 6th cycle over here. And it turns out that the intention was that the smaller cycles would give you a local communication. So maybe there's a little small cluster here that is working on something, and there's another cluster that's working on a different process. And eventually they communicate to combine results. So that was the idea back in the day when for interconnection networks. So what is known? So this graph, there's a lot of symmetry. There's a great deal of symmetry and other beautiful properties, structural properties of these graphs. So they're very interesting in its own right. So I'll describe some of these properties now. So this one is perhaps the most, this is what allows you to do a lot of the proofs. It's just this recursive structure where the previous case is embedded in PN, for example. So you have n-1 pancakes, that graph will be embedded in PN. And you can think about it as simply saying, if you leave the last pancake fixed, you just don't touch it, then essentially you're just moving the first n-1 pancakes. Therefore, you can see this embedding fairly easily. For example, here, you can see, you can look at the 6 cycles here. All of them have the property that they have the last character is fixed. So if you leave the last character fixed, then essentially you're moving with the remaining characters, and it's essentially the same as having one less pancake. So here we have a whole bunch of 6 cycles if you leave the last character, for example, fixed. And yeah, so this is the case for 4 pancakes, but if you only have 3 pancakes, it will look like a 6 cycle. Then you can also talk about the girth. So the girth is the length of the minimum cycle in the graph. And it turns out that it is 6 for pancake graphs. So it was shown at some point that it was the length of the minimum cycle in any of these pancake graphs is 6. So you won't have any cycles like 3 cycles, 4 cycles, or 5 cycles. It's also n-1 regular, and it's vertex transitive. So those 2 properties, these are very easy to see, I think. So n-1 regular, so like the degree of every graph, every vertex is n-1, and it's vertex transitive because essentially there's an automorphism that transforms any vertex into any other vertex, and this is all good. And this is another property that they showed in 1995. It essentially says that PN is weakly pancyclic. And what they mean by pancyclic, so pancyclic in graph terms means that you have every single cycle from length 3, so the simple cycle, of course, so a triangle, all the way to a Hamiltonian cycle. But this one is weakly pancyclic, means that you don't have some of the cycles. So essentially the weakly part means, well, okay, maybe you won't have 3 cycles or 4 cycles, but you will have all of them from the girth, from the length of the minimum cycle to a Hamiltonian cycle that will go through all of the vertices of the graph. So this was proven in 1995. It's actually a very nice, interesting property, which seems to hold for these generalized pancake graphs, which holds for these generalized pancake graphs. And I will mention that as well. So, yeah, so this result from 1995 showed up in this Journal of Parallel Computing. And again, the reason why it showed up there is because people were interested in these interconnection networks. And these are actually computer scientists, like these are honest to God computer scientists. And they, again, show that they argue that pancake graphs are made for good models for interconnection networks due to their sort of logarithmic diameter, having a whole bunch of symmetry, and having these cycles is actually useful for local computations, as I already explained. So there's other properties known about P sub n. So I'm using Bn to indicate the pancake graph of n vertices when you have a stack of n pancakes. So essentially you have n factorial vertices. But so like I mentioned, the cycles represent some local communication. There's only 1 6 cycle in Pn, and this is just this one. And then so k cycles have been classified for small values of k by Konstantinova and Medvedev. So that's actually the first reason. That's one of the reasons why we started talking to Elena, because she has a whole bunch of beautiful papers that have to do with cycle structures of the pancake graph. In particular, when they classify the smaller cycles. So they give a canonical forms for all the cycles of what they look like. And they also count them as well. So, and another, like I mentioned already, the girth of the pancake graph is 6, and that was shown by Campiao. I think it was 2011. And like I mentioned, PN is weakly pancyclic, so it has all the cycles of all length from the girth to one that will go through every single vertex, namely a Hamiltonian cycle. So in the 1979 paper where Gates and Papadimitriou gave the first non-trivial bound that I mentioned, the 1.666, they also presented another problem, which is called the burnt pancake problem. So in this particular case, the setup is that the pancakes, not only do they have different sizes, but each pancake has an orientation. So it has a burnt side and a non-burnt side. And when you're sorting the pancakes, you want to have them sort them in the respective order according to their size, but also in such a way that all of the orientations all matches. So like you want the burnt side all the way down. So it has a very nice setup in terms of sign permutation. So essentially what you do, a sign permutation is a permutation on the set from 1 to n, and also -1, -2, -3, all the way to -n. That satisfies the property that W of minus I is minus WI for every I, for every positive I. And usually we underline the negative entries. So just for simplicity in the notation, we underline, instead of saying minus I, we write I underlined. In this case, we just talk about, because of this property, that this anti-symmetry kind of property, how you define the sign permutations, you can refer to them using what is called window notation. So all you need to know is what happens to the first n elements. And because of this anti-symmetry, you know what happens to the rest. And in this case, the question is, like I said, for the pancake, for a pancake problem would be, again, what is the minimum way of sorting, minimum number of flips that you need so you can sort a stack of pancakes so that the orientation also matches. So in this particular case, you can define what they call a prefix reversal. I'm using the same term, but you can also call it a sign prefix reversal. Essentially, it's the same principle. You reverse the first I characters in your string of representing the permutation, but also you have to alternate the signs. So whatever was plus before now is minus, and vice versa. So I have a small example. So the graph that you obtain in this fashion is called the Pancake graph. And this is a very simple case where you just have two pancakes. But of course, it gets more complicated when you include the orientations. So let's take, for example, let's see this one. So this is 1 positive, 2 negative. So we can flip only 2. I mean, we don't have two pancakes, so we can only flip 2 things. So you can flip the first character and you get to this one. Remember, every time you flip something, you change the sign. And then if you flip the whole thing, the characters are going to be 2, 1, but the 2 should be positive and the 1 should be negative because you need to alternate the signs. So in this particular case, you get an A cycle. Of course, you can add more pancakes and things get more complicated. So this is what happens when you have 3 pancakes. It's a little difficult to draw some of these things just because you want to exhibit a couple of different properties. In this particular case, we wanted to exhibit the fact that it's also have this hierarchical structure, this recursive structure that I mentioned. If you leave the last pancake fixed, you can see copies of the smaller, copies of the graph with smaller pancake, with fewer pancakes. For example, you can see all this. This again is an 8 cycle. So you can see all of you can see a whole bunch of A cycles here as well. So there's one here that results from leaving just the last character fixed being 2. You can also leave the last character fixed being 3, and then you get this big A cycle here on the border, right? So it's the same kind of hierarchical structure where you fix the last pancake, and it's essentially like you have one fewer pancake. In that case, you see the multiple copies of the previous graph, in this case BP2 inside BP3. And the property is actually very useful when you're trying to prove things about the graphs. So the other reason why people are interested in this kind of sorting is because it has connections with 2 genome rearrangements. So this is very well-cited paper from 1999. Essentially, it's called Transforming Cabbage into Turnip. And they have a polynomial algorithm for sorting sign permutations by reversals. So in this particular case, so they have this one example in the book, in the paper, where this is like, so a genome and a particular gene, as I understand it, a gene has an on and off switch. So it's essentially a gene has two orientations. Either the gene is on or the gene is off. In that case, if you suppose that this is the genome sequence representing cabbage, and this is the genome sequence representing turnip, which is another, I think it's a vegetable. Then what they do in this particular paper is, well, a way that species evolve, one way that a species will evolve is by doing these flips, these reversals. In this particular case, though, not only prefix reversals, but they use any kind of reversal. So in this particular case, if you want to get from this sequence 1 minus 5, 4 minus 3 to 2, to 1, 2, 3, 4, 5. Then what they suggest here is, well, you reverse this 2, and then that becomes minus 2. And then you reverse this 4, and that becomes minus 4. And then you reverse this whole block over here. So they actually call it, it's called block reversals, where you take a block inside the sequence, and then you just flip it. And then if you do that, you're going to get 2, 3, 4, 5. So it turns out that one way of a species evolving is by doing these block reversals. So it's a little easier than the regular pancake problem because you're allowed reversals anywhere in the sequence. And they provide the first polynomial algorithm. I think it's actually quadratic. It's actually very efficient. And which is not, by the way, this is not known, like there's no algorithm known. Obviously, I already mentioned that it's NP hard in the case of the pancake problem if you use prefix reversals. But it's not known what happens if you just allow for any reversals. It's still not known if it's polynomial. Okay, but things seem to get easier when you allow for signs. So in this particular case, we have a efficient polynomial algorithm that will sort any of these permutations, sign permutation using block reversals. Instead of prefix reversals, block reversals. And this is one picture that should have been Nature 2004, and it's a little hard to see, but it is indeed illustrating flips, pancake flips. So if you look at the first 3 here, for example, so essentially they're denoting genes, in this case by colors and shapes. And they have, the orientation is being denoted by where you can see it's kind of like little tiny arrows. So the arrows are pointing one way or a different way. So in this particular case, you just look at the first 3 characters here, then you can see that they're pointing one way, and then you reverse them. They reverse these 2. So this character 1, 2, and 3, character 2 and 3 are reversed, and you get those 2. And again, this is a way of denoting how some species evolve. So they, kind of like this, the number of operations needed tells you how far away some species are evolutionary. It's not the only way this species will evolve, but it is one way that they do it. And you can make these beautiful trees where species are according to these block reversals. Okay, so what is known? So now we started looking at cycle structure for this burnt pancake graph. And the first thing that was known Girth results for very similar graphs like this. And then following a very similar procedure that Elena and Alex Medvedev did in their papers, we were able to classify small cycles for burnt pancake graph. So we have like 8, 9, and I think 10 cycles. Well, this one's a little long. So we only put, it's very tedious, and it's very, I don't think anybody would publish that, but I could be wrong. But we do have the classification for this. So for example, this is the number of cycles. This is all of the cycles in burnt pancake graph. There's only 4 canonical forms. And again, the point of this classification is if somebody gives me an A cycle in the burnt pancake graph, we can tell you what it looks like. It has to look like one of these 4 canonical forms. And we did something similar for 9 cycles. So there's 9 canonical, there's 2 canonical forms for 9 cycles, and they're given here. Again, the point of this is somebody gives you 9 cycle, we know what the 9 cycle looks like. And we have something similar for 10 cycles that hasn't actually been published because it just feels like it's not a very it's a very tedious proof where it's a lot of cases you have to consider. So we didn't really feel like writing it up super pretty. Anyway, so one application, so what do we care? One application that we found for this cycle classification is the following. So and actually this led to another project that is pretty interesting as well. So one application is counting the number of stacks that require exactly k flips to be sorted. So can I illustrate so essentially you should let Rkn be the number of permutations in a sense that require exactly k flips to be sorted on exactly k. How many are there? Well, so for example, I can ask this question, right? How many stack of pancakes require exactly one flip to be sorted? And the answer should be n-1 because there's only n-1 reversals. And those are the ones that are only one prefix reversal away from the identity. How about 2? How many prefix reversals and how many stacks of pancakes require 2 prefix reversals to be sorted? And the answer is actually fairly simple. Is essentially you say, well, from the identity, you can do n-1 reversals. And from each of those, you can do another n-2 reversals. The only reversal you cannot apply twice is the same reversal. You apply one reversal, you don't want to apply it twice because then you go back to the identity. So for each of these n-1 reversals, there's another n-2 reversals. So the answer should be this. Well, are we double counting? Well, the only way we would be double counting it would be if we had cycles that are of length 4 or 3, right? Because you might be thinking of multiple ways, multiple reversals that can, 2 different ways of applying 2 reversals that will get you to the same position. But because the girth is 6, we don't have any 4 cycles. So this actually is the real count. There's this many stack of pancakes that require exactly 2 reversals to be sorted. And then you ask the next question is, of course, what about 3? Well, this is a similar idea. So you have the n-1 reversals at the beginning from the identity. And for each of those, you have n-2. And then if you apply another reversal, the only ones you cannot apply are the ones you just applied to get there. So then you have another n-2. But you might be asking, what about this -1? That's because there's only one 6 cycle in PN. So we have to remove it. So these are all fairly trivial based on the cycle structure. The first non-trivial case is what happens when you have 4. So requiring exactly 4 flips to sort the stack of pancakes. And we actually came out with the result based on the classification that of small cycles. So 7 and 8 were used, the classification of small cycles for the pancake graph and burn pancake graph. So we actually use Elena's classification to get this result. This is the number of stack of pancakes that require 4 flips, exactly 4 flips to be sorted. And we have similar results for BPN that rely on the cycle structure on this characterization of small cycles for these graphs. Then, of course, actually this is a nice. This is like you can see that I always like. So the next question, of course, is what happens when you have 5? And if you have like the cycle classification, you can actually do the same procedure. It was a very tedious inclusion-exclusion procedure to get this polynomial here. So it turns out there's a better way to do it. So which I won't talk about, but this is computationally a nicer way to do it if you count different structures. But it was an interesting application of the cycle classification in terms of something purely enumerative. Okay, so what else do we know about cycle structures? So there was this result that I mentioned already. Let me just go back. Sorry about this. Where you have, so the PN for the regular pancake graph is weekly pancyclic, which means you have all cycles of length from the girth to one that goes through every single vertex in the graph, so namely a Hamiltonian cycle. So we wanted to prove something similar for the burn pancake graph, and it turns out that it actually is true. So the burn pancake graph will have all cycles from length 8, which happens to be its girth, to one that will go through all of the vertices, so a Hamiltonian cycle. And this showed up in 2019, and the proof is actually fairly reasonable. It's essentially using the recursive structure of BPN. So I can explain it in this picture, which is the key to the proof. It's essentially saying, okay, so suppose this is like big picture sketch of BPN, and then inside BPN you will have a lot of smaller copies of BPN -1. So this is the way to note it. So this is the whole BPN, And inside of this, because of this hierarchical structure, you have smaller copies. You have copies of BPN minus 1 embedded in the graph. So now we use induction. So if you assume you can have all the cycles that you want, and that would be our induction hypothesis. You can use all of the cycles that you want inside of each of the copies. Then what we had to do is come up with a cycle that will go through as many copies of BPN as you need to. So we have this like base, we call it base cycle. Essentially, this larger cycle will connect as many copies, smaller copies, right? As many copies of BPN minus 1 as needed. So what we do is just an inductive procedure, right? And then, so we combine the smaller cycles in each of these graphs, in each of the BPN minus 1s with the base cycle in a way that you get the right length. That's the way we prove this theorem here. So this is what is called weakly pancyclic. BPN is weakly pancyclic. So again, you can have all cycles or length A to 1 that goes through all of the vertices. And the sketch is right there. Of course, you have to be this bookkeeping that needs to be done. But essentially, this is the idea. You assume in your inductive, you first have a base case, right? So we use computers for that. And then you just for the inductive step, in your inductive hypothesis, you assume you have as many cycles as you want or need inside of the smaller copies. And then in your inductive step, you combine those cycles inside of each of the copies with a base cycle, one cycle that will go through as many copies of the embedded BPN minus 1 as you need to. And then it works out pretty nicely. So I think one thing that I think is reasonable, and it's another reason why people were proposing all of the scaly graphs as interconnection networks. They actually have relatively fewer edges than, like, you have the complete graph, you can find anything that you want, right? The complete graph will have all of the cycles because you have all the possible edges. But there's this measure for graphs that is called edge density, which essentially is this comparison here. So it's this ratio of the graph, the edges that you actually have divided by the edges that you could have in a simple graph. The maximum number of edges you can have in a simple graph is the number of vertices choose 2, right? So we can do computations and see that the density for PN is this one, which is, like, again, for the density for the complete graph would be 1, right? You just have, so the closer to 1 you have, the more edges you have in your graph. But the edge density for BPN is even smaller, right? So it's kind of surprising that these graphs have relatively few edges, but they have enough structure in them to have all of the cycles. So I think it's kind of impressive. It's kind of surprising to find all of the cycles in spite of the graph having fewer edges. So, okay, so what this led us to this. So Gates and Papa Dimitri consider Pancake that has 2 sides, like a burn side and a non-burn side. But then, of course, the natural question is, what happens if you have M sides, right? So we're going to essentially what it is you assume that you have M signs that would alternate. So as you reverse your prefix, you're alternating among all these M signs. So mathematically, what we're thinking about is essentially this group, the Girth product of CM and SN, where CM is some kind of cyclic group, and N is this, and SN is the symmetric group. So if M is 1, you get the regular Pancake graph. If M is 2, you get the burn Pancake graph, and so on and so forth. So in this particular case, the notation gets a little tricky. So we will be using these characters. We call, so in this particular case, the underlying permutation is 4, 2, 1, 3. So those are the characters, and each character has a sign, and the sign comes from the symmetric group on the cyclic group on 3 elements. So this 4 has sign 2, this 2 has sign 0, the 1 has sign 2, and the 3 has sign 1. And the generalized prefix reversals, or just flips, are defined in the way that you think they would be defined. So essentially, in this particular case, what we do is reverse the first 3 characters. So we have 4 to 1 become 1 to 4. and we alternate the cycle, the signs, right, according to the cyclic group. So in this particular case, the sign for 4 used to be 2, so now it should be 0. This is for cyclic group on 3 elements. So the sign for 2 was 0, so now it should be 1, and the sign for 1 was 2, so now it should be 0. All right. So this is how you get this generalized pancake graphs, and then you can get more graphs as well. So we were interested in understanding these properties. So again, this generalized pancake graph would be Cayley graphs on this group using the prefix reversals as generators. And like I mentioned, if you have n equals 1, you get the regular pancake graph. If m is 2, then you get the burnt pancake graph, and so on and so forth. And one difference that is interesting from everything else is, like, in this particular case, if m is bigger than 3, at least 3, then the graph won't be directed. And that's because in the past, right, the reversals here, the reversals for m equals 1 and 2 are also involutions. So you apply them twice and you get back to the identity, but not anymore if m is 3 or more. So if m is, like, then you have this, we consider directed graphs. And the last thing I want to say, I mean, no last thing, but, and also, it's also true that the edge density gets smaller as m gets larger. So again, there will be fewer relative edges for larger m. And these are some examples. I mean, such beautiful graphs. So this is for sequence for 3 signs and 2 characters. And you can see all these beautiful symmetries. And okay, so let me explain a couple of things. First of all, if you focus only on a red cycle, this is what I was telling you. So you fix the last character. In this case, let's look at this one here, the triangle on the top. This one has the 2, 0 fixed. So you're alternating only the 1. So it goes from, let's say, 1, 0 to 1, 1 to 1, 2, and back to 1, 0. And like I said, the graph will be directed because you apply the same reversal twice. It's not true anymore that you go back to where you started. And then you can have C4. And again, look how beautiful this graph is. There's a lot of symmetry going on. And you can have, similarly, you also will have this hierarchical structure that I mentioned before, where you leave the last pancake fixed. In this case, it will be a pancake and also a sign, right? Like you can, like, for example, this square here is the ones where you leave character 2 with sign 3 fixed. But you can also leave character 2 with sign 1 fixed, and then you get this other square. So it doesn't matter. You just have to fix a character and a sign, and you get the same hierarchical property or recursive property that we saw before, where you see the smaller graph, the graph with fewer pancakes embedded in it. Okay, so I will mention the results that we have for this graph. First of all, a couple of properties that are already known or are very trivial. So first of all, all of these graphs are Hamiltonian, and there's actually a couple of different algorithms that have come out recently that shows that all of these beautiful generalized pancake graphs are Hamiltonian. But it's not only that they're Hamiltonian, but they also provide a rule of how you get the Hamiltonian cycle. There's a couple of different algorithms that this group in Canada has come up with. This one is also trivial. The number of vertices is CM. Okay, so this is not trivial. But this is trivial. The number of vertices will be m to the n times n factorial. So you have n characters, and each of the characters has m symbols. So the count, this is the count that you would get. And like I mentioned, all of these graphs have this hierarchical structure where you just leave the last pancake, the last character, and sign fixed, and you get a smaller copy. You see several copies of the smaller CM ref product Sn-1 embedded in here. Okay, so what about cycles? Which is, we have all this beautiful cycle structure from before for the pancake graph and the burnt pancake graph. How much of that can you extend? It turns out that you can say a lot of it works out very similarly. So the girth, like I mentioned, is the length of the shortest cycle. So Campeao showed that if m is 1, the girth of the pancake graph is 6. If m is 2, then the girth of the regular pancake, the burnt pancake graph is 8. So if m is bigger than 2, then we showed, so that's Charlie and myself, that the girth of the generalized pancake graph is going to be the minimum between 6 and m. Obviously, you're going to always have an m cycle, right? So like you can see here, and you will always have an m cycle just because of the action of the cyclic group. The question is, can you find a smaller cycle? And yeah, we have, so we exhibited, we gave a 6 cycle that you can find in any graph. So it's either the minimum of 6 or m. And the way the proof works is very similar to how he proved his results. So because of this hierarchical structure, we look at like the smaller values of m here. So like you will have, like in this case, when he was proving his results, he started with P2 and BB2 that are both 6 cycles and 8 cycles respectively. And then he showed that there's no other shorter cycles. All of the 6 cycles and 8 cycles will be embedded in Pn for larger Pn or BPn because of this hierarchical property I mentioned. But then you use that structure to show that you cannot find any shorter cycles. So it's something similar. We do something similar here. So the paper is in the archives. It's under review right now, which takes a long time apparently. Okay, so this is for the girth. So we have a complete answer for the girth for any value of m. So it's complementing his results. So Campiao have the results for m equals 1 and 2. So we have the remaining results for any value of m. We know exactly what the girth would be. And then we started looking at the length of the cycles, right? Because we have, like I mentioned before, we have this weakly pancyclic property where you seem to be having all of these cycles from a particular length to Hamiltonian cycle. And we wanted to see if this was true for this generalized pancake graphs. So we did 2 things. One of them is we started to look, so we have implemented a beautiful algorithm for finding cycles, which is more efficient than just regular DFS or BFS. It's a little more complex. It's slightly better. And it turns out that finding cycles is a complicated problem too, right? So we just started to look at different implementations that people had, and we used it to look at this results right here. So this is computer search gave us this. Again, it was a little tricky. It's not like sometimes when people say computer search, I feel like they leave some of the details. Like it can be complicated computer search, like smart computer search. It's not just brute force. I mean, there's some optimizations that you need to do. Otherwise, it gets stuck fairly easily. So we found these numbers, right? So here is m is the number of signs, and then it's the number of characters. And we found that the existence of all of the cycles for this particular length that I mentioned. So for example, for 3 and 2, you have all of the length from 3 to 18, except for 5, 7, 11, 16, and 17, and so on and so forth. For m equals 4 and n equals 2, for the directed case, for the regular for the Cayley graph assist, you get all of this, the even numbers, all the even length cycles from 4 to 16, from I guess 4 to 32, except for 30. 30 doesn't show up, and so on and so forth. So when you see something like this and you try to prove it, first of all, you try to come up with a conjecture of what is the length of the cycles, but we don't have a conjecture just because you see the numbers, like they seem to be kind of arbitrary, like you might be thinking maybe it's at the prime numbers, but then you have 16, and I don't know, like it was difficult to us to come up with a conjecture of what cycles you will have. So in this particular case, yeah, so you can see all the even cycles, but theta, like theta doesn't show up. Okay, so what we did is, okay, so that it seems to be difficult to understand the length of the cycles that you have in the regular directed case. So what about the undirected case? So for the undirected case, all we do is essentially consider the underlying undirected graph. So in the graph that we have here, we have all these arrows. So we just ignore all the arrows, and then you get an undirected graph that way. In that case, we actually found that things behave a lot nicer. So we were able to look at some, like these patterns that show up pretty quickly. And so we make some conjectures. and the conjectures ended up being true. So this is the results that we have. So for if M is odd, then the generalized pancake graph is weakly pancyclic. So it has all of the cycles from the Girth to a Hamiltonian cycle. If M is even, then the generalized pancake graph has all even cycles from the Girth to a Hamiltonian cycle. So in this, so this you can like that's what we mean. For example, in this case, so if M is 4 and N is 2, you have all of the even cycles from 4 length, starting from one that has length 4 up to one that has length 32. So you have all of the even cycles. It is possible that all cycles will exist, that the proof doesn't preclude them. So there might be some odd cycles, we just haven't seen them, but they might exist. And so this is a summary of all of our results. So and then the Girth, like I mentioned, is the minimum of MN6. So this is these are our results from the paper. This is a summary of our results of the paper that is under review right now. And then it remains open what happens in a directed case. So yeah, so that's a little more complicated. I should mention here, I think, okay. So now where do we go from here? There's two questions. There's a couple of different things that we're exploring right now. First of all, so both Charles and myself started with Coxeter groups back when we did our PhD thesis. So we had this venue, this particular question that we had is like, what can we have a presentation for Coxeter groups? Let's just do type A and B, which are the most common ones. So this is the regular permutations, and this is the group of sign permutations. So can we have a presentation for the Coxeter groups of type A and B in terms of prefix reversals? And then yeah, so we have a presentation now for groups for these groups based on prefix reversals. But then the question is to, because we're not very versed in computational group theory. So is there something, now that we have this presentation, are there some techniques that can be used to give maybe establish some algebraic bounds to the pancake problem? So, or some other properties about the graph that comes from strictly algebraic points of view, but algebraic from the presentation. And then the other question that we have very recently, some numbers are still running, but we have started looking at the spectra of small Bernoulli pancake graphs. So by small, I mean in less than or equal to 5. The case for n equals 6 has been running for weeks and probably won't never be finished. But can the spectra provide some decent bounds for the pancake number? So there's always connections between the spectrum and some graph properties. But so I know there's going to be some bounds, but maybe not the best bounds that you can have. One property that we found is that we have seen the presence of integers in the for all the integers in this form, all integers in the interval from minus some number k to some number n, and we seem to see all of the as eigenvalues. We seem to be getting all of them from some negative number. This is only integer, by the way. You get other eigenvalues that are integers, but we're only trying to focus on the integer values that you get. So it seems that you're getting all of the as eigenvalues, every single integer from some interval, and we're trying to understand why. So Elena pointed out that this is known for the regular pancake graph for PN, and we're trying to look at that paper and trying to see if those methods can extend to Bernoulli pancake graph. So this is currently something we're working on. And I believe this is my last slide. So thank you. I don't have a thank you slide, which I should, but thank you very much for your time. And I'm happy to answer questions.
Okay, thank you very much for your presentation. Are there any questions to solve? Well, actually, I have some simple questions. First of all, as far as I understood, the generalized pancake graph set is the same as, say, M-sided pancake networks. So this notation is commonly used by Canadian researchers, say Savada, Williams, and Cameroon, right? Yeah, you know their papers. Yeah.
It's the same thing, yes.
It is the same. Okay. Then would you please show me the table with your results? It is one of the last slides. Yeah, this one. So what does it mean, red color for 30? What does it mean?
Oh, I just wanted to point out that you have all of the even cycles except for 30.
Uh-huh.
Yeah, I just wanted to point out that, yeah. So in this case, we have all of the even cycles, but 30 is not there. And I just wanted to emphasize that the only one that is missing is 30.
Mm-hmm. Well, say, I don't understand that for the directed case, the directed case is more complicated, right? Yeah. So what is unknown, but it is possible to understand in this case? I mean, is there just simple problem which can be solved, say, by student, by computational methods? What do you think?
We actually, yeah, we tried to make conjectures for the directed case in a couple of different questions, but we couldn't really find one. There was other than, I mean, we know that obviously the degrees and we break the transitive, all of these properties, but we don't have a conjecture for the cycles. We know that there's Hamiltonian, like you mentioned Sawada and Williams, they proved that there's Hamiltonian, all of these M-sided networks have Hamiltonian cycles, and they give you like algorithms for it. But honestly, as far as I know, we don't have an easy question for directed cases, because when we start thinking about the question, the conjecture, there's not enough. We cannot even formulate conjectures. I mean, if Charles is here, he might want to contribute something. But that's just my opinion, is like we're not even able to formulate conjectures for the directed case.
But it is Hamiltonian, right? Yeah, it is known.
Hamiltonian is known. That is known, yes.
Yeah. Mm-hmm. And you said that there are a few algorithms to get Hamiltonian cycle in this case, right?
Yeah, so you mentioned Sawada and Williams, and that is their group. They have one paper that showed up this year with more like one or two algorithms that do Hamiltonian cycles.
Right, at least last year it was published a paper by them in lecture notes in computer science about some algorithms on finding Hamiltonian cycles exactly in directed case, I think.
The directed case, yes. So that one is known. That is known. That yeah. Yeah. So actually, if you have students, it would be like it would be nice to formulate conjectures first, but we couldn't find one that was like we just didn't find enough patterns. We looked at these numbers and it's like, I don't know, I couldn't find a pattern.
But in the table, in the first table, M is restricted by 6, but for which M did you check computationally?
We check for all these values for M and N. So like for M, this is like, we have some partial results for others, but this whatever you see in the table is like completed. So like we looked at the whole graph for M equals 6 and N equals 2, and we did find all of the even cycles.
Yeah, I see. But if M is 7, did you do the same?
Oh, if M is 7, it did not finish. So he found some stuff, but not. It just got stuck at some point. It just wasn't able.
I see. Because of some computational reasons, right?
Right. It's just too large, and then he was running for a while, and then eventually, hey, you have to like stop running because we need the computer for something else.
Oh, I see. Well, and one more question. You said that the paper with this result is under review, but is it reachable on archive?
Yeah, it's in the archives. Yes.
I see. Okay.
Yeah, he actually was correct. We submitted to this CS conference, and they didn't. They said there's not enough algorithms in this paper. It's more like a combinatorial paper, so graph theory paper. So that's what we submitted to the graph theory journal. But yeah, so yeah. So we already got some feedback, but it's not CS enough for them.
I see. Okay. Thank you. Thank you very much. Any further questions to solve? Well, okay. If not, then let us thank again the speakers. Thank you very much. It was very interesting, even for me. I know something about this area, but you presented us a lot of some application in bioinformatics and computer science. Thank you very much. It was very interesting. Thank you.
And thank you to you for the invitation. And we used your results before, so I'm really happy that we got to connect.
I'm also happy that you are with us. Thank you. Thank you so much.